Hello, my name is Tushar Singh, and in this video we are going to discuss end semester examination paper of algorithm design and analysis. Let's get started. Question number 1. Analyze the time complexity of quicksort algorithm in average case and provide a step-by-step explanation of the sorting process. Quicksort follows a divide and conquer approach. It selects a pivot element from the array and partition the array into two sub-arrays, one of with elements smaller than the pivot and the other with the element greater than the pivot. It then recursively applies the same process to the two sub-arrays. A recursion tree for quicksort in which partition always produces a 9 to 1 split yielding a running time of O n log n. Note shows the problem size with pre-level cost on the right. The pre-level cost include the constant C implicit in the O n term. Here you can see the time complexity of quicksort in average case represented by a recursion tree which is split into 9:1 ratio, and the height of 1/10 ratio is log n base 10, and the height of 9/10 part is log 10/9 n, which give us the combined complexity of O n log n. The average case running time of the quicksort is much closer to the best case than the worst case in O n log n. The key to understand why is it to understand how the balance of the partitioning is reflected in the recursion that describes the running time. Suppose, for example, that the partition algorithm always produces a 9 to 1 proportional split, which at first blushes seem quite unbalanced. We then obtain the recurrence relation Tn 9/10 plus Tn/10 plus Cn. On running time of quicksort, where we have explicitly included the constant C hidden in the O n term, figure in the above slide shows the recurrence tree of this recurrence as we have studied earlier from this diagram. Notice that every level of the tree has cost Cn until the recurrence reaches boundary condition at depth log base 10 n equal to O log n, and then the level that cost at most Cn. The recurrence terminate at depth log 9/10 n O log n. The total cost of quicksort is therefore O n log n, thus with 9 to 1 proportional split at every level of recurrence, which intuitively seems quite unbalanced. Quicksort runs in O n log n time asymptotically the same as if the split were right down the middle. Indeed, even 99 to 1 split yields an O n log n running time. In fact, any split of constant proportionality yields a recurrence tree of depth O log n where the cost of each level is n. The running time is therefore O n log n where the split has the constant proportionality. Step-by-step explanation of the sorting process. Select a pivot. Choose a pivot element from the array. The pivot can be selected in various ways, such as picking the first, last, or the middle element of the array. Partitioning the array. Rearrange the array in such a way that the element less than the pivot are placed before it and the element greater than the pivot are placed after this. This step is often called partitioning. Algorithm is written here as you can see. The next step is recursive sorting. Recursively apply the above step to the subarray formed on the left and right side of the pivot. This means repeating the partitioning and sorting on the subarray on the left of the pivot and the subarray to the right of the pivot. Combine the result. Subarray are now sorted individually and combine the both subarrays. Base case, the recursive process continues until the subarray have size 0 or 1, in which case they are already considered sorted. This process of partitioning and recursive sorting the subarray continues until entire array is sorted. Quicksort time complexity of n log n is widely used in practice due to its efficiency. Question number 2. Critically evaluate Strasson's matrix multiplication algorithm and compare its time complexity with the traditional matrix multiplication method. Strasson's matrix multiplication algorithm is a method for multiplying two matrices that is faster than the standard matrix multiplication algorithm for large matrices. It is based on the divide and conquer technique, which involves dividing the matrices into some matrices and performing some operations on them. The time complexity is represented by the recurrence relation Tn equal to 7 n by 2 plus O n square, which can be solved using the master's theorem. And it takes slightly less time than the standard matrix multiplication, which takes O n cube, and it takes O n power 2.81, which can make a huge effect when we are multiplying large matrices. Here is the solution using the master's theorem, which yields us a time complexity of n 2.81. And the comparison between two, Strasson's algorithm is faster than the standard algorithm for large matrices because it reduces the number of matrix multiplication from 8 to 7 for each sub-matrices. Multiplication is more expensive than addition or subtraction, so reducing the number of multiplication saves time. Here is an example which requires 7 multiplication to get the result of two 2 by 2 matrices. Here you can see we have m1, m2, m3, m4, m5, m6, m7, which are the product of the each values in matrix A and B and represented in a special way, and adding subtracting these values generates C11, C12, C21, C22, which generates our final matrices C, which is represented here. Now question number 3, evaluate Prim's algorithm for finding the minimum spanning tree and provide a real world example where it can be applied. Analyze Hamiltonian cycle and provide an example of how they can be used in real life application. First we will discuss 3a. Prim's algorithm is a widely used and efficient algorithm for finding the minimum spanning tree MST of a weighted undirected graph. It starts with an arbitrary vertex and iteratively grows the MST by adding the closest vertex to the existing tree. The algorithm guarantees the resulting tree will be minimum spanning tree. Evaluation of Prim's algorithm. Time complexity. The time complexity of Prim's algorithm is V square using adjacency matrix of the graph and OE log V, where E and V are adjacent vertices respectively when using a binary heap or a Fibonacci heap. Correctness: Prim's algorithm consistently produces a minimum spanning tree, which is a connected acyclic subgraph that spans all vertices with the minimum total weight. Space complexity of Prim's algorithm is OV, which requires the priority queue or the minimum heap to efficiently affect the minimum weight edge. Additionally, it requires OV space for maintaining a set of visited vertices and their associated data. Here you can understand with the help of a diagram. Working of Prim's algorithm: determine an arbitrary vertex as the starting vertex of the MST. Follow step 3 to 5 till there are vertices that are not included in the MST. Find edges connecting any tree with the fringe vertices. Find the minimum among these trees. Add the chosen edge to the MST if it does not form any cycle. Return the MST and exit. Real world example of Prim's algorithm include: suppose you are tasked with establishing a high-speed fiber optics network in a city with multiple neighbors. The goal is to connect all neighborhood with minimum number of amount of cable while ensuring that every neighbor is accessible from any other neighborhood. Each neighborhood is represented as a vertex in the graph, and the distance between neighborhood represents the cable length required to connect them. By applying Prim's algorithm to this scenario, you can start with an arbitrary neighborhood and iteratively add the nearest neighborhood to the existing node. The algorithm will select the edge with the shortest cable length to connect the neighborhood, eventually resulting in minimum spanning tree that connects all neighborhood using the least amount of cable. The resulting minimum spanning tree obtained from the Prim's algorithm will provide an optimal layout for the fiber optics, minimizing the overall cost of cable installation while ensuring connectivity between all neighborhoods. Now, answer for question number 3, part B. Hamiltonian cycle, also known as Hamiltonian circuit, are path in graph that visits each vertex exactly once and return to the starting vertex, forming a closed loop. Analyzing Hamiltonian cycle involves understanding their properties, complexity, and limitation. Properties and complexity. Existence: determining whether a Hamiltonian cycle exists is in a given graph is NP-complete problem. This means that there is no efficient algorithm to finding the Hamiltonian cycle in a general graph. However, some specific class of graphs, such as complete graph, can be solved in polynomial time. NP-completeness. The Hamiltonian cycle problem is considered NP-complete because verifying the correctness of Hamiltonian cycle can be done in polynomial time. However, finding the cycle itself is computationally challenging. Complexity. The complexity of finding a Hamiltonian cycle grows exponentially with the number of vertices in the graph. The number of possible Hamiltonian cycle in a graph with n vertices is n-1 factorial, which increases rapidly as n grows. Here is the diagram where all the nodes are connected to each other and traversed exactly once. Real life application. One real life application that can benefit from Hamiltonian cycle is the organization of delivery routes for package or goods in logistic. Imagine a scenario where a delivery company needs to deliver package to multiple locations represented by vertices in a graph. The goal is to find the most efficient route that visits each location exactly once and returns to the starting point. By formulating this problem as a graph and applying algorithm to find Hamiltonian cycles, the delivery company can optimize its route and minimize time and fuel consumption. The Hamiltonian cycle will represent the optimal sequence of location to visit, ensuring that each location is served without revisiting any already visited location. Although finding Hamiltonian cycle is generally computationally challenging, in practical scenarios the problem can be simplified by considering constraints such as geographical proximity, time window for deliveries, or specific order dependency between locations. By incorporating these constraint, heuristic algorithm or approximation techniques can be employed to find near solution to the real-world logistic problem. It is important to note while Hamiltonian offers a theoretical concept for solving optimization problem, the complexity involved in finding them limits their direct application in large-scale real-world scenarios. However, the concept of Hamiltonian cycle and related algorithm can inspire the development of heuristic approach and algorithm for practical optimization problems. Question 4. Apply analytical perspective to develop a greedy algorithm for sequencing unit time jobs with deadline and profit. Discuss the advantages and limitation of this approach. A greedy algorithm for sequencing unit time job with deadline and profit is a method of scheduling a set of jobs that each takes 1 unit of time to complete, have a deadline by which they must be finished, and have a profit associated with them if they are finished before the deadline. The goal is to maximize the total profit by selecting a subset of jobs that can be completed without missing any deadline. Greedy approach. The greedy approach for this problem is based on the idea of sorting the jobs in decreasing order of their profits and then assigning them to the least possible time slot that does not violate the deadline. This way we prioritize the job that have higher profits and try to fit them in the available time slot. The steps for implementing the greedy algorithm are as follows: sort all the jobs in decreasing order of their profit, initialize an array of time slot with size equal to maximum deadline among all the job. Initially all slots are empty. For each job in the sorted order, do the following thing: find the least time slot I with that is empty and I is less than or equal to the deadline of the job. If such a slot exists, assign the job to the slot and mark it as filled. If no such slot exists, ignore the job. Here is a pseudocode for greedy job sequencing. You can have a look at it. Advantages. The advantages of greedy algorithm are: it is simple and easy to implement. It has a time complexity of O n log n using a sorting algorithm like merge sort or quick sort, where n is the number of job. It always gives an optimal solution for this problem as proved by Horn's theorem. The limitation of greedy algorithms are: it may not work well for other variants of problems, such as when the job have different durations or when there are multiple processors available. It may not be suitable for dynamic or online scenarios where new jobs arrive over time and need to be scheduled on the fly. It may not be flexible enough to accommodate other constraints or objectives, such as minimizing the total completion time or minimizing the fairness among jobs.